Morning, class. Happy Tuesday. As always, I hope that you and your family are doing okay. I'm sure we're all getting to the point where we know someone who has COVID-19. I hope that for some of you that's not the case, but anyway, the numbers are becoming a little bit staggering. But it's hard to focus, I know, but let's push on. So we're going to be looking at current and resistance. This is chapters 26, and this is going to be part 1. So hopefully you've been getting the other lectures. I'm getting famous on YouTube. Not really, but it's only in my dreams. But we're going to continue on. Lectures will be in 15 to 20-minute chunks. That's probably the best for me to upload onto YouTube, and also good for me as far as talking nonstop without some sort of interruption. I really miss the banter in class. I miss Lucas coming in 5 or 10 minutes late. I miss questions by Fox. I hope all you guys are doing okay. But let's plan to get together on Thursday just to connect and to chat for a while. Try to get a sense of how this course is going to wrap up. And I also want to get a sense of how your other courses are going, and what kind of innovative things the faculty are doing. This seems to work the best for me. Being able to lecture live on Zoom would be just about impossible. So this is as close as we can get to me being in class, as I've said before. The only thing is that we don't have the kind of wonderful interaction that I really quite love, and it breaks up the monotony of being in class for an hour and 15 minutes. Anyway, so let's get started. So up until this point, we've dealt almost exclusively with charges that have not moved, except for just a brief discussion on how capacitors charge up. We've dealt with charges that basically are static. That's why we've called it electrostatics. So we're going to relieve that restriction now. We're going to look at charges that are in motion. And this chapter is a short one. It's a bit of a respite. There's not a whole lot of new and complicated material in here. So for the next 2 or 3 parts, it should be pretty straightforward. I know the last several parts from chapter 25, some of those portions were complicated, and I'm sorry for that, but all you guys are bright and can handle that material. So as far as materials are concerned, they can be broken up when we look at their electrical properties. They can be broken up into 3, and probably more precisely 4 camps. So we have conductors, materials that can readily transport charges through them. We have insulators. And these are materials that cannot very easily transport charges through them. And then we have materials which are called semimetals. And lastly, materials which are called semiconductors. And so the difference between these guys is subtle and well beyond the scope of this course. But I will make mention of some of those differences a little bit later when we talk about semiconductors a little bit later in the chapter. So, for us, conductors are going to be typified by the metals, copper, silver, gold. Right? These are your classic insulator or your classic conductors, things that very readily conduct electricity, and we're somewhat familiar to them. As a matter of fact, we'll get into the reason for why copper in particular is a good conductor. We have insulators, materials like diamond, which is the consummate electrical insulator, plastics, and so there's a whole host of insulators that do not have, in our case, free electrons to be able to move through the material easily. Semimetals. So semimetals are an interesting group of materials. If you look at the periodic table, which I urge you to do, the upper right portion of the periodic table primarily contains materials that are primarily insulating. Right? You have the noble gases. You have nitrogen, oxygen, sulfur, the halogens. These are all materials that are basically insulating. And then you have this sort of stepped structure in the periodic table. So if you look at materials like boron, silicon, germanium, arsenic, antimony, tellurium, aluminum, polonium, all these materials reside on that little zigzag step in the periodic table. And those are your metalloids, or I'm sorry, your semimetals, or what are sometimes called metalloids. And so things like boron, silicon, germanium, etc. Okay, and then we have semiconductors, and we'll talk about those. Those are typically more complex materials, doped metalloids. Okay, so we have doped. You don't know what that term is yet, but I might describe it to you. Doped metalloids then can become semiconductors. So I just wanted to break up the materials into those basic 3 or 4 camps. So let's look at copper, and let's look at a sort of prototypical conductor. So let's take a chunk of copper. There's a pure cylinder of copper, and let's just pretend. Well, first off, let's let's look at its electronic structure. So copper is 29 in the periodic table. So it's Z equals 29. And if we were to do the Aufbau principle on copper, that is, if we were to fill the orbitals, then we would have 1s2, 2s2, 2p6, and that's 10 electrons. We'd have 3s2, 3p6, and now we have, if we were to fill this according to the Aufbau principle, we would have 4s2, 3d9. So we know from Hund's rule, and hopefully some of you remember that, and if we actually look at the 4s2, 3d9 shell, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's the 3D, here's the 4s2. So what happens in Hund's rule is that you recall that both the half-filled shells in the 3D, or a completely filled 3D set of orbitals is more stable than not. And so what happens is that one of these 4s2 electrons goes and fills the 3D level, and that we have an inversion of the energy levels, so that then we have 3d10, 4s1. Okay, so so what we have then is all of these orbitals are filled except for the 4s1 orbital. So the 4s1, right, contributes one unpaired electron, which is basically untethered. It's basically untethered, which means that it's free to move in the copper lattice. And it is this 4s electron that contributes to electrical phenomena in copper. So let's redraw this. Let's move down here. So here's our chunk of copper. Here's our chunk of copper, which has all of these. Each copper then is going to contribute one 4s1 electron, and so we have what is commonly called a Fermi sea. We have a sea of electrons that are basically free to move within the copper material, or copper lattice. And so let's look at one of these electrons. Here it is. Here it is. Before we do so, let me introduce a couple of definitions. So we're going to be looking at charges on the move. So charges that move from one region in space to another constitute or form what is called a current. A current. So whenever we have moving charge, whenever we have moving charge, we have a current. And so by definition, the current, which is sometimes given as capital I or lowercase I, is by definition the change of charge that moves past me per unit time. And if we were to look at this instantaneously, that is in the limit that we close down the observation time window to be very, very small, then this becomes equal to dq dt. So the current, uppercase I or lowercase I, and you'll see both, is going to be defined as dq dt. And that's worth a box. Okay, so charge on the move is going to represent a current. So now, if we were to look at one of these copper free electrons, and if we were to somehow tag it, right? So we're going to shade it in as red so we can follow it. And if we were to look at it over time, then it's going to move. You know, it's going to go here, 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 maybe here, here. And so when it's doing this, it's moving for a time, and then it is colliding with other stuff in the lattice. Could be colliding with other electrons. It could be colliding with the nuclei of copper surrounded by all of its complete orbitals. But in a simple way, it's just going to move for a short period of time and then collide with something. And so this motion is actually prolific in science. We call it Brownian motion. And it was first discovered by Robert Brown, who actually was a botanist. And what Robert Brown did is that he looked, right? He looked, and you should look him up on Wikipedia. Robert Brown, botanist. He looked at pollen grains. In water under a microscope. And what he noticed was that the pollen grains were in constant motion. Pollen grains were in constant motion. And he had a hard time explaining that because if they were in water, say in a little puddle, of water on a slide. It was hard to imagine that the water was in motion because the little puddle of water looks pretty still to the human eye. But he noticed that these pollen grains were in constant motion. And he reported on this. Right? So he reported on this phenomenologically, which means that he just noted that it was occurring and offered no scientific explanation. But it took several years until Einstein developed the mathematics, along with a Polish physicist, Smolakowski, developed the mathematics for Brownian motion. And it was actually a French physicist who redid Brown's experiments. His name was Jean Baptiste Perrin. So he actually did a redo of Robert Brown's experiment. And it was actually among the first experiments that provided evidence for the atomic picture of matter. And for his accomplishments, he actually won the Nobel Prize in physics in 1926. Seems like a simple experiment, just kind of watching pollen grains in water, but the physics of that is incredibly far-reaching. As a matter of fact, models of Brownian motion are now used for finance, in particular the stock market. And so the mathematics is very far-reaching. So in any case, though, getting back to our original model, if we were to follow an electron, as a matter of fact, let's tag this the way I tagged it before. So here's an electron which I'm able to tag red, for instance, and I watch its motion. On the average, even though it's moving constantly, on the average, it wouldn't go anywhere. So if I were to watch this at some time t0 and then come back later, an hour later, it's going to be in the general vicinity of where I left it, right? So there'd be no net motion. Okay, but I do want you to appreciate that in a solid hunk of copper, that this sea of electrons is constantly on the move. So what happens now if I were to put a battery on this. Okay, so here we are. I'm going to stick a voltage source. This side's positive. This side's negative. As a matter of fact, let me just change that around because I need some space. So let's just change that around. So I'm going to make this side positive, this side negative. Now again, the assumption here, this is certainly well before the discovery of the electron was discovered. And so let's just assume here that this is a positive, what I'm going to call a positive mobile charge carrier. A positive mobile charge carrier. Okay, so it's positive and it can freely move. And so we know, given what we talked about many times before, right, charge carriers want to move from region of high electrical potential energy to low electrical potential energy. That's tantamount to moving from high electrical potential to low electrical potential. And if we now were to watch this charged entity, which now we're going to assume is going to be positive, right? So in our heart of hearts, we know that in copper they're negative. But for now, let's assume that these are positive mobile charge carriers. And if we were to watch that, then again, right, it's not going to travel very far before colliding into something. But what we'll notice is that if we watch it for a long time, it's actually going to move from here to there. Okay, so it's actually going to move from left to right. Okay, so if we were to watch this for a long time, this charge carrier now would actually not be in the same vicinity where we started watching it, but it would be downstream, so to speak. Okay, so it would move. And again, if it's going to move from here to here in a given time, then it has a speed, and so we're going to call that the drift speed. Okay, so we're going to call that the drift speed. All right, V subscript D. Now, what is noticed is that we have two speeds here, right? We have the speeds between collision. So we have the speed between collisions, and we have the drift, and we have the drift speed. Now the speed between collisions actually could be quite high. As a matter of fact, it's going to be on the order of 10 to the 6th meters per second. The drift speed now is going to be far, far less than 1 meter per second. As a matter of fact, it could be on the order of 10 to the negative 6 or 10 to the negative 7 meters per second, right? So it could be, right, depending on the material, it could be as small as 10 to the negative 6 to 10 to the negative 7 meters per second. So really small. This drift speed is really small. And again, it's due to the incredible number of collisions that this mobile charge carrier is suffering as it moves through the material. Now, I want you to appreciate, and we'll end this chunk right after this statement. I want you to appreciate that if positive charges are moving this way, that is from left to right, then then really the electrons are moving this way. So electrons, this would be the direction of electron movement. This is electron movement, and this is the direction of positive charge movement. So we're going to assume in all of our discussions that current is the movement of positive charge. And positive charge moving in one direction is the same as electrons moving in the opposite direction. And for you chemists, right, that should not be unfamiliar to you, because you probably addressed this when you looked at electrochemistry at the very end of your course in freshman year. So this is a good place to stop. It's I guess I'm probably encroaching 20 minutes here, and so next time we meet, we'll continue our discussion. You should be reading the text. You should be reading the text, looking at the checkpoints, working the example problems, and lastly, beginning to tackle the problem assignments at the end of the chapter. Okay? Okay, people. Stay safe. Take care of your loved ones, and I will see you shortly. Take care. Bye.